Welcome back to the lectures on Introduction to Multi-Agent Systems. For every graph, much like the adjacency and the Laplacian matrices, we can also write up something that's known as the incidence matrix. In today's lecture, we'll learn what exactly is an incidence matrix, how do we define it, and we'll also take a look at a practical system whose behavior we can describe using the incidence matrix. So let's get started. Consider the diagraph shown in this figure. With the diagraph, we know that we can associate three fundamental matrices known as the adjacency, the out-degree matrix, and the Laplacian degree matrix here. So let's quickly write up the values here. Node number 1 has outgoing edges to 2 and 3. So these will be the corresponding entries. Node number 2 does not have any outgoing edges. So this is the adjacency. Similarly, node 3 has outgoing edges to 4 and 5 only. The rest of the entries are 0. Node number 4 has outgoing edges to 2 and 5. And the rest are 0. And node number 5 does not have any outgoing edges. So based on this, we can quickly write up the degree matrix. Node number 2 has a degree. Sorry, node number 1 has an out degree of 2. Node number 2 does not have any outgoing edges, meaning its out degree is 0. Similarly, this and again this. Based on this, we can again quickly write up the Laplacian matrix -1, which is something we learned in the previous lecture. It is T out minus A, so that's how I'm filling in the entries. 2, -1, and -1. Node number 4, 0, 2, and -1, and again, this is all zeros. Closely, the matrix A has a dimension of 5 cross 5. Now, why 5 cross 5? Because there are 5 nodes here. Again, the degree and Laplacian are derived out of the adjacency. Hence, they again also have a degree of 5 cross 5. Meaning, all of these matrices, adjacency, the degree matrices, and the Laplacian are derived out of the properties of the vertices. Is there a way in which we can create yet another fundamental matrix associated with a digraph or a graph such that, or which uses the information of the edges that we have in the network? Can we construct any such fundamental matrix? The answer to that question is yes. And that matrix is known as the incidence matrix. Since all of the matrices that we see here do not give, while implicitly they do give information about the edges, but not explicitly. So this is addressed by introducing something that is referred to as the incidence matrix. So let's quickly write up or define what is an incidence matrix. But before that, before we actually start defining what exactly it is, let us first write up a few conditions under which the definition of an incidence matrix makes sense. We say let us consider a digraph G consisting of a vertex set V and an edge set E, such that the following properties hold. What are the properties? The first one is G has n number of nodes. Second property is something that is generally something that we don't specify very often. That is, G has m number of edges. Again, this is a property which we do not specify. Furthermore, we say that G does not have any self loops. Okay. Under this framework or in this paradigm, we now present the definition of the incidence matrix. The incidence matrix will denote it as a matrix P, or it's often written in this manner, B, is defined as or let's rather write it in this manner. The ijth entry, let's now call it the ikth entry of the incidence matrix. The incidence matrix P or we can also write it in this manner, is defined as follows. We already have an indexing of the vertices, say V1 to Vn. What we now do is we also index all of the edges in the network, E1 to now Em. Then we construct the incidence matrix in this manner. Along the rows, or rather, this is what the rows denote. Every row is associated with a certain vertex, and every column is associated with an edge, E1 to Em. Now, let us focus our attention on the kth column. Obviously, it pertains to the kth edge in the network. And let us look at some ith vertex. Let's denote this as Vi. Let us also have yet another vertex, some Vj. This be a Vj. Now, according to the definition or of the incidence matrix, if we pick any column of this matrix, we denote all of the entries of the column as equal to 0 if the edge Ek is not incident with the vertices. So let us say our edge Ek, which is given to us, starts at Vi and ends at Vj. Then every other vertex here, other than Vi and Vj, will now have an entry equal to 0. And what happens to the entries associated with Vi? This entry is always equal to +1, and the entry here is equal to -1. So let's write it. This is equal to +1, and this is given by -1. So this is how we define or how we construct the kth column of the incidence matrix. We can follow a similar style for every other column as well. We just figure out, because every column is associated with a certain edge, we look at that edge, we figure out what node it starts from and where does it end, or basically also known as the head and tail. So for example, these are some things which we have defined before. This is known as the head, this is known as the tail. So the head of the edge always has an entry of +1 and the tail has an entry of -1. So based on this information, we are now ready to formally define the incidence matrix. So let us keep this expression here, or this matrix here, and write the incidence matrix B is defined as follows. So we'll define the ikth entry. What does it look like? It is equal to +1 if Vi is the head of the edge of the edge EK. Because here remember that K represents the column. So K is associated, let's highlight it, K is associated with the edge EK. Now, with this information, let us write the next entry. Suppose Vi is not the head of the edge. Then there's yet another possibility. This entry is equal to -1 if now Vi is rather the tail of the edge EK. If it is neither the head nor the tail of the edge EK, then that entry is equal to 0. Meaning, in every other case, this entry is equal to 0. So now, let us try to define the adjacency matrix. Let us try to write up the entries of the adjacency matrix for the example that we saw before. So in this network, we see that there are 5 vertices and 6 edges, meaning the incidence matrix has a dimension of 5 cross 6. So these are associated with the vertices and the columns are associated with the edges. Okay, now let's look at the first edge. The first edge has node number 1 as its head, meaning this entry here will be equal to +1. And its tail is given by node number 2, meaning this will be equal to -1. And as given in the expression in the formula here, the rest of the entry become equal to 0. Hence, we place 0 here. Let's look at the second edge. The second edge starts at node number 4 and ends at node number 2, meaning we place a +1 here and -1 here. And the rest of the entries are again equal to 0. If we look at edge 3, it starts at node number 1 and ends at node number 3. The rest are 0. Similarly, E4 starts at +3 and ends at 4. The rest of the entries are again equal to 0. E5 now starts at 3 and ends at 5. The rest of the entries are 0 again. And E6 starts at 4 and ends at 5. So now this is what the incidence matrix looks like for the given digraph. Notice here, it is quite different from the adjacency, degree, and the Laplacian matrices, in the sense that now we have edges appearing, or explicit information of the edges appearing as the columns of the matrix. So now let us ask ourselves the following question. We already had the fundamental matrices, the adjacency, degree, and Laplacian. So why was there a need, or is there at all a need to have the incidence matrix? Does it help us in perhaps expressing certain system behaviors, or why exactly should we study them is the question. So let us try to answer that question. We will now try to understand the motivation behind studying the properties of the incidence matrix. In order to do that, we'll start with the same example that we saw before while studying the Laplacian matrix. Let's start here in a new page. Okay, and also let us start first by constructing an electrical circuit. Okay, now let us add a few resistances in some places. And suppose this is a current source in the network, which is driving our resistances. Let's write up the values. Say this is R1, R2, R3, and R4. And say this is R5. Suppose this current source has value of I0, meaning the current source is trying to drive a current of I0 through the circuit. Okay, we have these. So now what we'll do is we'll try to construct a graph out of it. And in order to do that, we must define the vertices and the edges, or the nodes and the branches of the electrical circuit. So these points in red are the nodes, obviously. So let's mark them as V1, V2, V3, and V4. So these are the nodes, and the branches would simply be, so these are all the branches. All of these are branches. Now, let us ask us this question. Is this network a directed network or undirected network? So when we talked about the definition of the incidence matrix, let me take you there again. Here, we talk about the head of an edge and the tail of an edge, meaning we're actually talking about a directed graph. So how do we associate directions in the case of our electrical network? The answer to that is, we'll associate, or the direction of a branch, we'll consider it to be the direction of the current that flows through that branch. Meaning, let us now arbitrarily mark the directions of the current. Suppose as the current enters node V1, it splits up into these points. Suppose this is our edge E1, and the current flowing through it is some I1. And similarly, the current flowing here is I2, and this is our edge E2. Without loss of any generality. Okay. Now let's first quickly write up here. This is I3. And this here is I4. And without loss of any generality, let's assume that current flows in this direction, and we denote it as R5. And let me also index all of the edges. So we have this edge as E1, this as E2, and let's denote this as E3, this is E4, and this is E5. Do we have any other edge? Yes, we do have, which is this edge, E6. Okay. Now, when we were studying the Laplacian matrices, we realized that the potential differences between the nodes could be easily expressed using the Laplacian matrix. So let us write up the fact. The potential differences between different nodes in a network can be studied using Laplacian matrices. So this is something that we saw in our earlier topic. So now I would ask the students to pause the video right here and try to figure out by themselves if in any way can we use the incidence matrix to describe any of the relations of the variables that are associated with the circuit. Okay, I hope you have tried it out and also figured out that the current relations can be easily expressed using the incidence matrix. So how do we do that? So in order to do that, let us first write out what is the incidence matrix associated with this graph. We saw that there are 6 edges. 1, 2, 3, 4, 5, and 6. We can write it in this manner. V1 to V4, there are 4 nodes, and then there are 6 edges. Let us start one by one. The first edge, as we can see here, starts at V1 and ends at V2 because that is the direction of the current. So starts at V1, ends at V2. The rest of the entries are 0. E2 from V1 to V4. The rest are again 0. E3, V2 to V3. E4 is V4 to V3. E5 similarly from V2 to V4. And E6 similarly starts at V3, V3 and ends at V1 in this manner. Okay, so this is what the incidence matrix looks like for a given circuit. Let us do some quick manipulations to it and observe a few things. Let me write up the matrix here again and multiply this matrix by the following. I3 up to I6. So now I've constructed a vector here consisting of the currents that flow through the circuit. This is a 6 cross 1 vector because there are 6 branches and 6 different values of currents flowing through them. This is I1. Let me just write I1 to I6. What is this equal to? If we evaluate it, this is equal to the following. The first entry here is I1 plus I2 minus I6. And the second entry is minus I1 plus I3 plus I5. And this is equal to minus I3 minus I4 plus I6. And the last one is equal to minus I2 plus I4 minus I5. So note here that we can also observe here that I6 is actually a constant which is equal to I0. But for now, let us just write it as I6. So let us write it here. I6 is equal to I0. Now what what do these currents represent? Well, so that we can easily understand, let me bring the circuit here and draw it right here. Let us take a look at this circuit again. What do we observe? Let me just increase it a bit more so that it's clearly visible. Okay, this is better. Let's look at the first node here. The first node has an incoming current I6 represented as minus I6 here, and there are two outgoing currents I1 and I2 as denoted here. So meaning the first expression that we see here is equal to 0, meaning this is nothing but the Kirchhoff's current rule and is simply equal to the following. Shift this here slightly and write it. V times the current vector I is simply equal to 0 4 times 4 cross 1. We know that it is equal to 0 for the first node. So this simply represents the total current at the first node. Now, does this represent the current flowing through the second node? Let's quickly verify this. I1 is the current which enters, minus 1, I3 and I5 are the current which are exiting. And obviously, so this is also correct. It should be equal to 0. Similarly, I3 enters node V3 and the current exiting are there are two currents which enter the node 3. The first one is I3 and the second one is I4. So we see that both of them here have negative sign and I6 is the current leaving. So this is equal to, this has a plus sign. Similarly, for node number 4, I2 and I5 are entering. And what is leaving or exiting is I4, which has a positive sign. Hence, when we use the incidence matrix and multiply to it the vector of currents flowing through the branches, then what we get is exactly the current at each node. And this expression, according to Kirchhoff's current rule, is equal to 0. Just to remind you, here, please take a note of this fact that I6 is actually equal to I0 here. So when we actually substitute it, we get an equation that the variables here are I1 up to I5, and so meaning what we can further rearrange this in this manner, V times I. So if we are willing to reduce its dimension slightly such that we include only 5 of the edges, in that case, what we will have is 5 currents. So let me call it B prime. What is B prime? B prime is now the incidence matrix of the reduced system, which has 5 edges. Which system is that? It's just this sub-network here. So B prime has now a same number of vertices, 4, but now lesser edges, meaning we now have only 5 currents that we are interested in up to I6. So this expression will no longer be equal to 0 because of these relations that we have from here. So if we evaluate I1 plus I2 is equal to I0, hence we can simply write it as some constant, perhaps, maybe some f here, which may or may not be equal to 0. Either way, the incidence matrix in both the cases, B and P prime, it allows us to study the current relation within the network. And not only that, it can be written in a very concise manner. These relations can be written very concisely using the incidence matrix, which motivates us to study incidence matrices and understand and apply them to different applications. So this is just one of the applications that we apply to. So one interesting thing again to observe here is, if we look at this entire expression one more time, what do we have here? The input to the system is the vector of all the currents in the system, and the output is equal to the current at each node, meaning the output is something that pertains to the vertices, current at each vertex. And this here, I, is the current flowing through each branch, meaning when we input to B some information about the vertices, we input to B some information about the edges in the network, and the output that we got is some information about the vertices. Hence, to summarize, we can write the following. The incidence matrix B is a map from edge-based variables to node-based variables. This is a very useful information. Now, obviously, in a similar manner, we can say that if you're looking at B transpose, it is a map from node-based variables to edge-based variables. Okay. So this was an introduction to incidence matrices, and we also saw an example where we can actually use the incidence matrix to describe the relationship between the different variables in the system, which was the case of the electrical network. In the next lecture, we'll study some properties associated with the incidence matrix. So with this, we'll end today's lecture. Thank you.